we're going to talk about the second part, part 2 of the reader. Basically, it's about system identification and adaptive control. If you think about what we have learned, well, we have explained it last time. We have so far been assuming we know the plant when we design controllers. In practice, the plant, the plant may be unknown, or the plant may even be time varying. So in these cases, if you want to do model-based control design, we're going to encounter some difficulties. In practice, you can obtain these plant models basically from 2 approaches. Either you model by physics, you model by Newton's law, conservation of energy, etc., etc. For example, if the robot pick up an object, the weight of the object will influence the model of the robot. But if you know exactly what's the mass of the object that it picks up, then you can incorporate that into your model. So that's the first part, modeling by physics. And the second part is this. Usually, modeling by physics, you would want to obtain systems that are of low order. For example, Newton's law, F equals ma. So that's a usually second order, first order system. That's you start from there and you build up small pieces by small pieces, and you finally obtain a large model of the plant. Another way is, suppose you just want to. It's like you are doing interview to the system. You feed the system through some input that you carefully prepared, like a series of questions, and you see how the system responds to your questions. And based on these input and output data, you can obtain some models of the system. This is called system identification. So it's a data-based system identification. In this case, you won't be concerned too much about how the system, the physics of the system looks like, but just want to know how the input and output behavior looks like. Sometimes these two are combined together. For example, first you model by physics, but there are parameters that you don't know. This is very common. And how you can obtain the parameters is by doing some input-output analysis and then find the parameters. So this is very important and extremely useful in many applications, which we have seen here, unknown plants, time-varying plants. And most often, you're going to have this problem. So you don't know the disturbance. Maybe you know the disturbance structure, but you don't know how the disturbance parameters look like. And in this case, you have to use adaptive control. Adaptive control means you let the system adaptively find the knowledge, the information, either of the plant or of the disturbance, then perform control compensation to handle these cases. That's the basic picture for system identification and adaptive control. I would like to start the analysis by reviewing something that you have seen, but I haven't officially introduced it yet. System modeling. So, for example, when we say a plant, when we write the plant transfer function as a, let's say, 0.2 plus, this is just an example, 0.2 plus 0.5, z to the power of -1, 1 plus 0.9, let's say. When we say the transfer function of the system looks like this, and then we have input, let's say UK, going into the system, and I get an output, YK. So essentially, if you write out this difference equation, you're going to see YK equals 1 plus 0.9, z -1, 0.2 plus 0.5, z -1, UK. Again, this z is a delay operator, means z -1 UK equals UK minus 1. So it's a delay operator. If you write it out, shift this denominator to the left-hand side, you're going to get yk plus 0.9 yk minus 1 equals 0.2 uk plus 0.5 uk minus 1. Okay? So this final step is going to reveal what I want to say today. So yk equals negative 0.9 yk minus 1 plus 0.2 uk plus 0.5 uk minus 1. Okay? So it equals 0.9, 0.2, 0.5 negative yk uk minus 1. Okay, so look at this result, this final result. This is the main message for this slide. The output at time k is going to be a linear combination of the this is yk minus 1, this typo, yk minus 1. The output at time k is going to be a linear combination of the previous output and the inputs information. And these are linear combination, right? These coefficients here, 0.9, 0.2, 0.5, are the coefficients, are the parameters of the Planck model. So if we want, we can write it this way. We can define this as a theta. We can define this parameter as a theta, and then this data vector as phi. The notation is going to be phi k minus 1, my notation. You see, maybe yk is better. Let me use yk notation. Okay, so here it's saying output is a linear combination of the data you measure previously and then the input you have at time k. This is called let me start a new page. This is called the regressive form of the Planck model. So you say essentially this is a model of the Planck. It's giving us an alternative representation of the transfer function model. We write it this way, called the regressive model. And more formally, for the case of a general system, let's say the Planck model is z to the power of -1, b and a. These BAs look like polynomials of z to the power of -1. Okay, b and a look like this. Before, let me ask you one question. I know I put a general, when I say that this is a general form of the transfer function, I put a, the first coefficient of a as 1, and I claim this is a general representation. I didn't put this, I didn't say a0 here, but instead I said this is 1. Why can I do that? Just a simple question. Yeah, so if I have, everyone sees that? If I have a0 here, I can divide both the numerator and denominator by a0. Then I will get this normalized form. This is a usual way to write a general transfer function model. Because in this case, you avoid the confusion of, because you will avoid this confusion. So if you write it in a general form, let the first coefficient be a0, then it's possible to say a0 equals 0. And that will give you inconveniences when you analyze the transfer function model. You won't even know what's the order of the system, because if a0 is 0 and b0 can be 0 as well, then the order of the system will reduce, because you can factor out z to the power of -1 both in the numerator and denominator. That will give you all kinds of inconveniences. So we'll do like this. That's possible. So that's why. So following what you said. If in the transfer function, if it is in the continuous time case, it's inconvenient to write it this way. This is not convenient because it's possible these are both of them are zeros, and you got these confusions of orders. Mm-hmm. Oh, so if you have this one. Mm. Oh, so you're saying in the continuous time case, yeah, that's right. Mm. In the discrete time case, it's a little bit different, if you see that. That's a good observation. So, yeah, indeed, in the continuous time case, A0 being 0 is necessary sometimes for writing out the integrators. But in the discrete time case, let's look at this more together into more details. So in the discrete time case, you don't have things like this. Maybe the most common way is most closest case is this one. But this one you can write in the discrete time case without problem because you can write it this way. What we have been writing is this. Let's say a first order system. You see, you can make A0 to be 0, B0 to be 0, and B1 to be 1. Then it's going to become Z to the negative 1. See? There's no A0 here. Okay. All right. Yeah. So discrete time case is a little bit different, and that expression is a general expression. Okay. So now you see, even if for this discrete time case, what we said is exactly correct. You can write. Let's work on equation 1. You can write this Planck dynamics by, now you have yk plus 1. If I shift az minus 1 to here, az minus 1, yk plus 1 equals bz minus 1 uk. Okay? So just write these polynomials, factor out these polynomials. You're going to get, now this time I'm going to write it in a little bit faster fashion. So the result is going to be yk minus 1 equals, factor out, when you factor out these polynomials on the left-hand side, shift it to the right-hand side, you're going to get negative signs. You're going to get negative a1, z negative 1 operated on yk plus 1. You're going to get this. Then minus a2, yk minus 1. Then all the way to negative an, yk, let's say, what's the index? I think it should be yk plus 1 minus n. So then plus bz minus 1 operated on uk is going to be b0 uk plus b1 uk minus 1 plus all the way to bm uk minus m. So just in the exact same fashion as what I did in the first order example. So everyone, so can see this? Okay? So the essential message is exactly the same. You see, all these information, yk, uk, all these informations are the collected information about the system, either from the measurement or from the input. So we can write it negative yk all the way to negative yk plus 1 minus n. Then uk minus m. Okay, we can write it this way. The coefficients is going to be a1 to an, and then b0 to bm. Okay? So again, we can write it in the regressive form, where, now, let me officially introduce. This called phi k is the regressive vector. Regressive vector. And these coefficients, plant coefficients, are called, usually denoted as theta, called plant parameter or parameter vector. But the central message is, first of all, is a linear system. If you when you see this, you should be immediately seeing that this is a linear system. The coefficients are these, and the output depends linearly on the previous output and the control input. Okay. So finally, we can write it in the simple form: theta transpose. It's just for convenience. When we write theta, theta means a column vector. So actually, theta is this one. Just for convenience of notation. So theta is a column vector. Both theta and phi are column vectors. You can write it that form. So this is what we have just derived. The simple regressive form of the plant dynamics, where you have this no measurement, no vector, regressive vector and measurement element. The goal is to, if theta is unknown, you have this plant model, and you want to estimate this theta based on the information of phi k and phi k plus 1, these informations. Okay? So this is our assumption. We assume we know the plant model, but we don't know the detailed values of these plant parameters. The system identification process is actually pretty intuitive, in the sense it's based on this basic idea. If you don't know theta, then try something, try to assign some values to theta, and then try to see what it will give us. And if this is wrong, if y hat, this is called an estimation. We assign some values to theta, and we call this theta hat. Then we try to estimate y of k. And if this y hat doesn't match y of k, then we make improvements on this estimation, plant parameter estimation. Okay? So the notations are explained like this. Hat means, hat usually means estimate. It's similar to an observer case. When we say x and x hat, we want x hat to estimate x. And then this index k here means the estimate of theta at time k, as I wrote down. Okay? So this is the basic idea of estimation and correction in system identification. Okay? In a more, the most simple way, the simplest way of doing plant identification, parameter identification, is to do least squares. But this is not the only way. This is the simplest way to start with. It works on this performance index for these squares. You see, pay attention to the notations here. JK means I want to estimate the plant parameter theta hat k based on all the informations I can collect from time 1 to time k. So that means I have y0 to all the way to yk, and I have this phi all the way to phi k minus 1. So I am estimating theta hat k based on all these informations that I can collect up to time k. Okay? So can someone tell me what is, if I want to find the best estimate, what is the exact solution of theta hat k in this case? So when you see a quadratic form of something, start thinking about whether it has an exact mathematical solution. If I just give you this is the cost function, does this guy has an exact mathematical solution? What is the best estimate theta hat k to solve this problem? Yeah, it's actually in the title, it's least squares. So how would you solve a least square problem? Theta hat k is the minimizer, is argmin of jk. Okay? given y0 to yk phi y1 phi 0 to phi k minus 1. So if you want to solve this unconstrained optimization problem, just take the partial derivative. This is a quadratic function, so you can just take the partial derivative and then get the solution. So set it to 0. There's a few places that you need to pay a little bit of attention when doing this. So you may have seen this or you may have not seen this, but let's do this together. So when you take the partial derivative of jk, partial jk, partial theta hat, you're gonna need to do is actually a summation of terms. So you take partial derivative of individual terms inside the summation sign. Then you're gonna get let me write it out actually. yi square. So I'm gonna write out this square function first. Minus theta hat transpose k phi I minus 1 phi transpose I minus 1 plus minus 2yi phi transpose I minus 1 theta hat. Okay, so there's only one thing I want to mention here. When you factor out this quadratic function, this term, I just want to mention one thing about this term. This is a common trick. So when you factor out this, you're going to have this term square. So just pay a little bit of attention that this guy is exactly this guy. Can everyone see that? I write it in a different form, but these two are exactly the same. These two are equal. Why is that? Can you see? So this guy equals theta hat transpose phi I minus 1, then times itself. Right? Is this a scalar or vector? It's a scalar, so it equals exactly its own transpose, right? These two are exactly the same. So in the end, it equals this guy. Okay? So writing it in this form, you see it's a quadratic form of theta hat. Okay? So take the partial derivative of this whole thing to this guy, and then set it to 0. You're going to arrive at, and let's do this very quickly together. So you're going to get, the first term doesn't depend on theta hat, so the partial derivative is going to be 0. You're going to have summation, first term doesn't depend on theta hat. The partial derivative of the second term would be 2 phi I minus 1 phi I minus 1 transpose theta hat k. And then the last term is going to be minus 2 yi phi transpose phi I minus 1. Okay? So if you want, you can check the dimensions. The partial derivative of these guys, of the last term, for example, should be a vector. So this is a vector. So it's not a transpose here, but it should be no transpose. Okay? So that's the solution of, that's how this minimization problem can be solved. Simple minimization problem. So if you set it to 0, you're going to get summation of 1 to the k 2 phi I minus 1 theta hat k equals summation from 1 to k. So this is a scalar. I can shift this one to the right-hand side without problem. There's going to be a 2 here. Okay? So finally, noticing that this is a matrix. This matrix is a matrix. So you can operate the inverse of the matrix on both sides to get this one finally. That's the final result here. So let me ask one question. Is this matrix Fk, even the inside, is the matrix inside this summation junction, is it positive definite or positive semi-definite by observation? Definite? For example, if you want to test, you can set k to be 1 for the simplest case. If it contains input. But that still, I think, not that rigorous. Even if your input is not 0, it can still, it's not guaranteed this is going to be positive definite. Yeah. Maybe it's best. So when you write this solution, you have to be careful. So look at this. If I set k equal to 1, then the inside, the summation is going to be phi 0, phi 0 transpose. This matrix, is it positive definite or not? It's not positive definite, actually. So you can try many examples. Even if it's 1, 1 or 1, 1, 1, 1, 1 like this, it's not positive definite. Oh, here. So this is actually, the rank of this matrix is always 1. This is a rank 1 matrix, actually. So for example, like this one. You can set it, for example, so you want to consider x transpose x, whether this is going to be positive or not, right? Set x to, for example, 1, negative 1. Then this is 0. So it's 0. So non-zero x, but 0 output. So be careful. Anything, any matrix that looks like this, A transpose is not full rank. It's not full rank at all. The rank of this guy is always 1. Okay? So be careful. This matrix, this summation of matrix can be not positive definite, and it can be not invertible. That's the first observation. The second observation, however, is when this k is pretty large, when this k becomes pretty large, this summation will give you full rank. Okay? So that's one thing you can observe from this solution. So if you solve it this way, you have to be careful whether this matrix is invertible or not. It may not be invertible. Okay? So I'm going to discuss something else, something alternative way to do this, which will give a little bit more simplification in the solution concept. Let me mention another thing. Let me mention another, for example, if this matrix is very large, for example, 10 by 10 matrix, okay? The computation here is going to be pretty, okay? So a least square solution, this is a least square solution, is very straightforward. You can derive the solution very easily, but you have to be paying attention about whether this guy is safe to invert or not. And you're going to be careful about the computations over there. Now, what I want to talk about now is recursive least squares. So I will explain what recursive means in a short moment. But suppose at time k plus 1, okay, so let's see the difference here. At time k, you are solving this optimization. You are solving this least square problem. Then the concept of this recursive least square is consider at time k plus 1. You do the same thing. You want to estimate the Planck parameter again. So what you want to do now is you want to use as most information as possible. Okay? You want to use the, for example, the output information from 1 to k plus 1. So you are extending the information you can use in this minimization problem. Okay? I think I have a little typo here. This should be k plus 1. So you want to estimate the parameter theta based on all the information up to k plus 1. So you can solve exactly the same way this least square problem. Okay? You can obtain exactly the same formula. But in this time, you're going to have everything that's indexed by k is going to be shifted to k plus 1 over here. Okay? So this is the solution. This is the improved solution. Improved solution compared to theta hat k, because you are using more information in this estimation problem. Okay? It turns out if you want to do this, you don't need to do this very complicated inverse problem. It turns out the solution of theta hat k plus 1 simply equals this guy. You can simply obtain the result by adding some correction term to theta hat k to your obtained solution at time k. That's the central idea of this is why it's called recursive least squares. So it's an iterative process. You improve the result step by step. So this is the main equation we're going to be focused on, and I will explain why this equation holds. Okay, so everyone gets this basic idea? You want to use at time k what information you are using, and at time k plus 1 what information you're going to be using. So let's spend some time to see details of this this recursive formula. Now what we have obtained, let me rewrite, for convenience, let me rewrite the solutions of the problem at k plus 1 over here. Phi I minus 1, phi I minus 1 transpose inverse, and then summation of phi I minus 1 y I equal to 1 to k plus 1. Okay? And we are calling this matrix, this inverse matrix, as f k plus 1. Okay? So let's do a little algebra and focus on this term first. This term equals I going from 1 to k phi I minus 1 yi plus this additional term phi, the index, be careful, should be k, and then y k plus 1. Okay? Now, look at this one. This one looks very familiar because when we write theta hat k equals fk fk summation of I to 1 from 1 to k phi I minus 1 yi. So these two are exactly the same. So I can write this guy then equals fk inverse theta hat k. So put it here. We're gonna get let's see, fk plus 1 inside. I'm gonna have a fk inverse theta hat k plus phi k yk plus 1. Okay, so far so good. Now do one more step, and then things will be, I think things will be almost clear. Fk plus 1, fk, what does fk equal to if you follow the notations we have been using? So fk is going to be the summation from 1 to k, then the inverse of that. So fk inverse, fk inverse is going to be summation from 1 to k phi I minus 1 phi I minus 1 transpose, which is going to be equal to, now look at here, summation from 1 to k plus 1 minus, what's the index, should be k. Okay, and this guy equals fk plus 1 inverse, right? So I think here, so far we have explained everything up to this step. We're right now here. Fk plus 1, and then inside it's going to be Fk plus 1 inverse minus this guy times theta hat k, then plus phi k yk plus 1. Okay? Then finally, you just need to factor out this part. Then you're going to get itself times its inverse. Then it's going to be identity times theta hat k. And then over here, you're going to get fk plus 1 phi k yk plus 1 minus minus this guy here. Okay, so fk plus 1 times phi k times theta hat k times phi, which is equal to, as we have explained, this guy equals this guy. Okay, so arriving at this final result, let's take a moment to see what's the intuition behind. So we have explained when we introduce the plant models, if you remember, we introduced the regressive form of the plant model, which is theta transpose phi k. And then we introduced this sort of estimation of y by this guy. So you see, exactly, this is an estimate of yk plus 1. So based on the errors of this estimation, we are making improvements to the previously obtained result, theta hat k. And then the central idea of these squares is it actually provides us an optimal gain, if you will want, an optimal gain for this estimation error. And this gain is obtained from the This gain is obtained from here. That's the least square solution, recursive least square solution. Okay? So these intuitions can be written, more formally written as follows. So I have copied down the equation we have just derived, equation 10. More formally, we can define these estimations. This is the estimation of y, and this is the estimation error. Okay? So I'm using a notation of y naught here. We will later see. This is called a priori estimate. Okay? So the name comes from this. A priori, it means when we estimate yk plus 1, notation here, we are using our estimate, we are using our plant parameter estimate, the information at k. So we are using the last step, the result from last step, to estimate, to predict the current step. This is the idea of why it's called a priori estimation. Okay. Now, finally, this is what we have obtained. This is the error, estimation error. This is a arrow-based recursive formula for. If you do this way, you see, we won't have to solve a large matrix inversion problem here, but instead we are just accumulating our iteratively improving our result over here. Okay. So if you are very careful about the notations, you're gonna see that fk equals this guy. Okay. So when I say it's going to avoid the matrix inversion, you might be confused why I can say that, because there's a matrix inversion here. Okay? So our next result, I'm going to show you that this guy, this fk plus 1 matrix, also looks like something fk, let me use minus, some update term. Okay, so in the next slide, I'm going to show you that this inverse matrix inversion, indeed, we don't have to do that. We can do this by this, again, iterative formula that shows as follows. That's the main goal of this slide. Okay, so it turns out fk plus 1 is going to be equal to fk minus this this update part over here. Okay. So essentially, I'm going to show you 1k plus 1 this guy is going to be equal to 1k okay, so let me explain the intuition here. So it turns out when you are considering the inverse of a matrix that consists of a bunch of summations together, okay, it turns out you can do this inverse by, you can decompose this inverse by whatever use up to time k, okay, and then minus some other terms. So more mathematically, this is what I mean. If you are considering the inverse of some matrix A plus some added term BC here, turns out the result is going to be the inverse of A. So it's going to be the inverse of A minus some terms that related to BC. This is a general version of the matrix inversion lemma. Okay? So you can verify that this is true by doing, for example, you can do A plus BC times this whole term here. You can see, you can verify that this is identity. So this is actually the inverse of this guy. But we won't be doing that in the class. You can do this as a homework or something. I want to show you, however, I want to show you the intuition behind this. Okay? If you have, let's suppose BC is some positive definite matrix. So let's assume that the size, roughly, I say the size of the matrix it's increased from A to A plus BC. So if you have something that's increased, if you have, let me do a scalar version. So if you have, let me do a scalar intuition. If you have, for example, 1 plus 2 times 3, you do the inverse of this guy. It's going to be equal to 7, 1 divided by 7. Okay? So this 1 is roughly the A here. And this A inverse is going to be 1 inverse, so it's going to be 1. You see, when you increase the size here, the inverse is going to decrease in size. The inverse is decreasing from 1 to 1 divided by 7. Right? So very similarly, for the matrix version, if you are increasing from A to A plus BC, then the inverse is going to decrease. Okay? It's going to be A inverse minus something. This is roughly an intuition of this matrix inversion lemma. Anyone has questions about this? So take a moment to think about this intuition while we work on this special case of this guy. So we have explained fk plus 1 equals the summation from 1 to k plus 1, the inverse of this guy, and then which is going to be equal to, so summation from 1 to k plus 1, phi I minus 1, phi I some transpose equals summation from 1 to k, phi I minus 1, phi I minus 1 transpose, plus okay. So you see, this matrix is increasing in size. So the notation is going to be fk plus 1. This is fk. This matrix increases in size. So the inverse of this matrix is going to intuitively sort of decrease in size. So it's going to be something minus term here. Okay? And the minus term, exact formulation of the minus term, the update term here, comes from the matrix inversion lemma. Okay? So treat this as A here, and then treat this as the BC in this matrix inversion lemma. Okay? So where are you guys confused? Mm. Mm. So here is just a here. So yeah, just for calculating this, because when you want to do this, you need to know what's fk plus 1. And this equation is exactly telling you how to calculate fk plus 1 based on all the, you don't need to do the inversion, just use this. Okay? And the detailed steps of obtaining this is just doing this matrix inversion lemma. Okay? So let me do this now. Let me do this. So up till now, if we summarize what we have obtained, summarizing, we have obtained theta hat k plus 1 equals theta hat k plus fk plus 1 phi k epsilon 0 k plus 1 with fk plus 1 equal fk minus also, if you want to check that this equation is correct, you can check the dimensions first. So this will help you to understand the structure of the equation here. The bottom here, it's got to be phi transpose f times phi, because only this way you can obtain a scalar that's going to match the dimension of 1. And on the top, you have to produce some matrix here. So inside, it should be phi times phi transpose. Then on the left and on the right are f. So do a dimension check if, for example, in the exam, you have to write down this equation yourself. So up till now, we have obtained this. Usually, there's an alternative writing of these equations just for different preferences. Some people want to write it in this form. Some people prefer writing this phi k transpose. So instead of fk plus 1, we use information just containing fk. It's going to be fk phi transpose phi k epsilon 0 k plus 1. Okay? So for computation, it turns out you can use this equation or this equation. Both are fine. Okay? And let me do this. So let me now explain that this equation 1, let's say equation star and the equation star 1, they are equivalent. Okay? So essentially, we just need to show that this is equivalent to this matrix. Okay. So how would you, if you look at the result, look at these three equations here, and are asked to prove that this is equivalent to this, how would you proceed? It's actually pretty, it's not complicated. How would you show this is equivalent to this? Fk plus 1 phi k equals, in the end, has to equal to Fk phi k 1 plus phi k transpose. Okay. So anyone has any suggestions? Substitute this to here. Let's try. So Fk, that is going to be phi k, so I'm going to multiply it inside, minus Fk phi k transpose Fk phi k divided by 1 plus phi k Fk. Okay? So your proposal is exactly the answer that I was looking for. So it's going to be this guy is equal to 1 plus phi k transpose Fk phi k. On the top, it's going to be Fk phi k plus, let's see, which order should I choose? So I think I can choose Fk phi k times this guy, phi k transpose Fk phi k. All right? So this is the first term, and then minus the second term, minus the second term. But this term, it has the same denominator, and then minus Fk phi k transpose F phi k. You see, this term is canceled out. All right? So the remaining part is only this. Okay? So this, we have thus shown that the original expression can be written in this form as follows. Okay? So for notation purpose, we're going to be calling this set of equations as a PAA, parameter adaptation algorithm. Okay, how we adapt the parameters. So you see, this is a recursive formula. So you have to initialize the equation at some point. So theta hat 0 is your initial guess of the parameter vector. If you know, for example, some rough values of the mass of the system for the damping coefficients of the system, you can set it here. If you don't know, you can set it to 0 and then let the system run. Okay? And then similarly for this guy, for the matrix F, okay? You see F, from here. You see, from here, if you are making improvements, if you are reducing this error, if you are doing it in the right way, you are reducing this error, intuitively, what should F be? What should F be? Should F be increasing or decreasing if you are doing good estimation here? So if you are on the right track, you can put less control over the equation here. So should be decreasing as you move along. You get better result here. So if you see that, then when you assign the initial value of F, you had better assign it to be large enough so that when you keep reducing f, you have some values to keep the equation running. So one way to assign is to put an identity matrix as F0. Well, the elements is a very large scalar numbers. Okay? So these are the basic ideas for system identification. If we want to do a quick review, we would say this is what we have done. First of all, the very fundamental result we have to keep in mind is this alternative representation of the plant model, and then the concepts of how theta is actually obtained in the least square sense. So these are the important facts. Summation from 1 to k yi minus theta hat k transpose phi square. Okay, these are the most important parts of this recursive least square as problem. Okay, and throughout this derivation, we use these concepts of estimation of the parameter. I mentioned this is called a priori estimation, prediction, and this is a priori estimation error. Okay, it has a special name because it has a brother or sister called a posteriori prediction and a posteriori prediction error. So it's written this way. They look very similar, but pay very special attention to the writing here. Okay, so a posteriori prediction is using all the information when you predict the yk plus 1. You are using theta hat k plus 1 to do this prediction. Okay, so let me ask you a question. First of all, should this be a better prediction or not? Intuitively. Yes, right? Intuitively, because we are using more information to do this estimation. Now, if this is the better prediction, why don't we use this in the estimation? Why don't we use, for example, when we write down the equation, so when we write down the PAA, it looks like this. Plus fk plus 1, phi k, epsilon 0, k plus 1. If this is the better prediction, why don't we use epsilon? This is a notation for a posteriori error. Why don't we use it here? Calculation time. That's one factor. Someone else wanted to say something, I heard. There's another reason. Calculation time is one reason. So look at, maybe let me use let me give you one hint, which is, so this is one hint. And then the second one is fk plus 1 equals summation from 1 to k plus 1 yi, no, not yi, phi I minus 1, phi I minus 1 transpose inverse, and epsilon 0 k plus 1 equals. So these are the hints. Think about why. So the final conclusion is that you can't simply use this here, although it's a better estimate. So look at, for example, oh, it needs memory. That's memory. Let me see. Probably can handle. We can handle memory. But there's another fact here. So if you want to do this, if you want to do y hat, if you want to do this a posteriori estimation, so you need theta hat k plus 1. If you need theta hat k plus 1, that means you need the information of yk plus 1. Because if you are doing estimation based on all the information of k plus 1, you need this guy. Okay? So now it becomes, now comes the confusion part. It becomes bizarre because, in the sense, when you do, so this is the not feasible way. If you want to do that, it becomes, the process is immediately going to become bizarre in the sense, now, when you do this guy, you need yk plus 1, right? And actually, you need theta hat k plus 1. Now, you see, originally, this update equation, all the things on the right-hand side. Let me take that back. Originally, everything here, this estimation, original way of writing is theta hat equals theta hat. Okay. This guy originally. This guy is using yk plus 1 as well, but it's using this. Okay, these are the two equations. Now, this equation you see definitely is implementable because you have theta hat k plus 1, and then you on the right-hand side you can update it by itself. But this guy, you won't be able to implement this because you see, you want to obtain this. It's like I don't know, chicken and egg or something. So you won't be able to implement this equation at all because you want to obtain this, but in your derivation, you are using it itself. Okay? So keep in mind that this a posteriori information is not for implementation. When you implement, use this equation. But when we use this guy, these are for important for analysis. For example, stability and convergence. Important for stability and convergence analysis. Okay? These are, we're going to be using a posteriori information soon. But keep in mind which one we are implementing and which one we are not. Okay? So, to give you some intuition, actually you already see some intuitions earlier. So, we have explained that this estimation, a posteriori estimation, which equals yk plus 1 minus y hat k plus 1. Okay? This y hat is a better estimate compared to y hat 0. Okay? So this error should be relatively smaller than this error here. This is the main result for this page. So the final conclusion is that we can mathematically show that this guy is smaller than or equal to this guy. Okay? And how detailedly, how much it's smaller than this is explained by this equation. So because it's 1 plus phi k transpose fk phi k, which is always non-negative. So you see, the denominator is always larger than 1. So the whole thing is going to be less than or equal to epsilon 0. Okay? So the obtaining of this equation is by doing the following steps. Okay? I think I won't detailedly explain every step, but instead, look at the result here. You can obtain information of arrows by multiplying phi transpose to this equation. Because when you do phi transpose theta hat, you get immediately the estimation of the parameter. And you do phi transpose times theta hat k plus 1, you get the a posteriori using information up to k plus 1. Okay? So do this multiplication. So this is multiply theta phi hat k. And then from here to here, if you want to obtain the arrow, you just subtract y by its estimate. So subtract y k plus 1 on both sides. You can get this result here. So by doing that, you obtain this final result. And again, massage these two terms together. You're going to get 1 plus phi transpose f phi minus phi transpose f phi. So in the end, you're going to obtain this equation. Just a just linear algebra. There aren't many tricks I want to mention here. Okay? So if you see this result, keep in mind about this equation here. If you see this equation 13, and then recall, for example, actually I have it here. Look at equation 13, and then look at the equation box. Okay? Look at these two equations. Can anyone give me a simplification of equation box by using equation 13? So it contains this guy, which is this guy. And it contains this, which is this. So we can simply write in equation box to theta hat k plus 1 equal to theta hat k plus fk phi k epsilon k plus 1. Okay? So this is the a posteriori version of the parameter adaptation algorithm. Okay? I mentioned is useful for stability analysis. Okay. One reason is that you see this guy is a little bit more simpler than the previous parameter adaptation algorithm, and when doing stability analysis, this is going to be pretty useful. Okay. I think this will be the end of today's lecture. We're going to talk about next time about forgetting factors, which is a very important part for system identification. Okay, so I have office hours today from 1 to 2:30, and if you have any questions, feel free to come to me.